So, good evening, everyone. Myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, and I welcome you all to the ninth live session of the NPTEL online course, Basic Principles and Calculations in Chemical Engineering, course instructed by Professor S. Majumder from IIT Guwahati. Let's get started. So, some general information about these live sessions is that these sessions will be held every week on Tuesday from 7 to 9 p.m. Just a minute. Hello. So, these sessions will be held every week on Tuesday from 7 to 9 p.m. And the access of the recording of these live sessions has been made available to you. And you can also access it through my YouTube channel. The structure of these sessions will be that first we will go uh, over the uh, overall walkthrough of the lectures for the corresponding week, and which is the week 9 this time, and then solve some sample problems which are related to your assignment, which will help you in solving the same. So, lecture 27 dealt with for the week 9, it dealt with material balance of transient process. So, what are transient processes? Firstly, so we will firstly go through the some recap of the general material balance. So, this is the general material balance equation. So, A accounts for, I'll write it here, A accounts for accumulation is equal to I is input, sorry, minus output plus generation minus consumption. So any material which is coming in and going out from a process, the general material balance equation for the same will be like this. Anything accumulated will be equal to some that material coming in minus that material going out. Plus, if it is there is some reaction in occurring in the system, so whatever the generated is added and whatever the consumed is subtracted. So what are transient processes? They are that process variables change with time. And in this term, and in these processes, accumulation, so this is written here, accumulation term cannot be neglected. So, general material balance for this process is written here. So delta M is the change in mass, suppose, and so the units of this equation is, suppose if mass is in kgs, so kgs only, because delta M is kgs. And this is rate of mass in. So that will be, suppose, kg per second. And delta T, if you multiply that with, and delta T will be in seconds. So again, this term becomes kg. You see the unit of all the terms is consistent. If you are writing an equation, you need to make sure that the units of all the terms are consistent. So this is also, the unit is also kg here. Same goes for this kg. So this is whatever mass is coming in, mass rate coming in into the delta T, minus mass rate going out into delta T, change in time. Then plus, if this is the rate of generation. So rate is given, suppose it is given in kg per second, suppose. So again it will be cancelled with delta T, so we get kg here as well. And then this is rate of consumption, which will be subtracted. So if we take delta T common and take it to the left hand side and put limit delta T tends to 0. So this is what we get. So the final equation is written here, dm by dt. I'm just rewriting it. M dot in minus m dot out plus rg minus rc. Some people write this rg as rg dot because they want to show this is also changing with time. But rate of anything, suppose if we are given rate is kCa, so the unit of this is basically mole per liter second. So it is already with respect to time, so that's why I've not written dot in the upper portion here, uh, as we have written in m dot. So that's why some people write it as r dot g. I have written rg only. So I just want to explain how do you write material balance for a transient process using an example. So suppose this is a system, and this and the inlet flow rate is given by nu naught, and the density of the fluid flowing in is rho, and the concentration of A reactant is Ca naught in this, and it is purely Ca naught here. And if you see, whatever is coming out has the concentration Ca, the density is again rho, and the outlet flow rate is nu, which is different from nu naught in this case. And in the reactor, this is the condition again. So Ca is again the concentration of A in this reactor, rho is the density, and V is the volume of this liquid in this. And this reaction A given B is taking place. So suppose if we are to write the overall material balance, firstly we start always with the overall material balance. In this case, it is necessary as well. Why? It will be clear in a moment. So we start with whatever is coming in. So whatever is coming in is nu naught. But this nu naught will be in meter cube per second, or suppose liter per second. So this is volume per time. The unit is volume per time. So we need to multiply it with density. So this is firstly I write the general material balance. A is equal to I minus O plus D minus C. So in this case, there is an inlet, there is an outlet. Nothing is generated currently, and there is no consumption as such as well. So this is because of for the overall material balance, overall fluid which is flowing. So we can write whatever is coming in is again rho into nu naught. Whatever going out is rho into nu. And what will be dA? So mass inside this reactor will be rho into V, and that will be d rho V by dt. This is the accumulation. So this is not nu, mind you. This is V, capital V. So this is how you get the first equation from the overall material balance. As you can see, because this mu naught and nu are different, so this moreover, just a minute. Moreover, what we can do is take this rho out because rho is constant. Uh, Rho is supposed to be constant for fluid because they are incompressible. So rho gets cancelled from all over. So we get final equation as dV by dt mu naught minus nu. So because this nu naught and nu are unequal, so they do not get cancelled, and we don't get dV by dt is equal to 0. We don't get this. So if was dV by dt is equal to 0, that means the volume does not change with time. But here we see that the volume changes with time. So next will be the component material balance. So material balance for A. So that will be again A minus, so something is coming in, something is going out. Nothing is generated for the case of A, but something is being consumed. So we write whatever is coming in. So this was the whole fluid. But if you want to write uh, the concentration of A coming in, that will be mu naught into Ca naught. How that comes to be is that we can see this mu naught is meter cube per second in terms of unit. I'm trying to explain, and Ca naught will be suppose mole per meter cube second. So meter cube per meter cube gets cancelled. This will be mole per second only. So I need to just make this clear. Whatever material balance equation you are writing, in the previous slide, I showed that this will have the units as kg. However, this, all the terms in this equation will have the unit as kg per second or moles per second. Okay. So here, this term has units moles per second. Whatever is coming out will be again mu naught into C, nu into Ca. Something is getting generated, and suppose this is a first order equation. So this is Ra. So minus of Ra minus Kca into, now this again, this is mole per liter second. So you need to multiply it with volume. So this is Kca. Again, here we write what will be the mass of A accumulated inside a mass of A built up inside the reactor will be Ca into V, mole per liter into liter. So this liter get cancelled, mole, and because there is by dt in the denominator, so it will be Ca into V. So this is the material balance of A. But as you can see in the previous equation, we could take the rho out and get it cancelled, but we cannot do the same for V here. Why? Because V is, from this equation we saw, it is uh, changing with respect to time. So it is not constant. So this opens up as Ca dV by dt plus V dCa by dt equals mu naught Ca naught mu Ca minus Kcav. So these are the two equations that you form, and then you further solve it to get your answer. Whatever the unit, whatever the numbers are given to you, whatever numerical values are given, you can solve it. So because these are with respect to time, so there will be some initial condition given to you. For V at time is equal to 0 will be given to you. C Ca at time is equal to 0 will be given to you. So this is how you solve these equations further. So that is how you get these equations for the transient process. I have shown you with an example. So here what happened was the inlet flow rate and the outlet flow rate were different. So that's why the sum of the mass was getting accumulated. Suppose if nu naught is greater than nu. So what would happen? Nu naught, if nu naught is greater than nu, so more will be coming in, but less will be going out. So this tank will get filled up. Suppose if nu naught will be less than nu, so less will be coming in and more will be going out. So this tank will start to empty. That, so intuitively you can also see the volume of this uh, volume of the fluid in the reactor will keep on changing with time if this condition is followed. And this is one of the example of transient process. Another example of transient process can be the nu naught is equal to nu, but already some liquid or some fluid is already present in reactive. So that is also another example. Those examples have been solved in the lectures. So we now move on to the unsteady state energy balance. So we looked at the unsteady state or transient state material balance. Now we look at the energy balance. So this is the general energy balance equation given to you. So this is the accumulation term. This is whatever is going in minus whatever is going out, plus this energy is the summation of heat content plus the change in kinetic energy plus the change in potential energy, and this is the work done, rate of work, not work done, this is rate of heat and this is rate of work. So for closed systems, we see that d by dt of pressure into volume is almost equals to 0. So that's how we get dE by dt is equal to du by dt is equal to dH by dt. And for the closed system, the equation is shown here. So now we start with some sample problems. So first question is the material balance equation for unsteady state process is given by. So we need to choose the correct option here. So we know from previous knowledge that accumulated is equal to input minus output plus generated minus consumed. So I guess this is the correct option here. Next question, for a closed system, dE by dt is equal to du by dt plus is equal to dH by dt. So is this true or false? So we saw from the previous slide that this is a true statement because dPv by dt for solids and for closed systems, sorry, for closed systems it is 0. So we can write it as just a minute. dPv by dt for closed system is equal to 0. So we can write H is equal to sorry, H is equal to U plus PV. But if you take the differential, so this dP by dt is 0, so we get du only. So we can write this here as well. So this is a true statement. Next, for solids and liquid, Cp is equal to Cv as dPv by dt is equal to 0. So du is equal to dH by dt. Yes, this is a correct statement as well. For solids and liquids, the relation for Cp is equal to Cv as they are mostly incompressible, and that's why we get dP by dt is equal to 0, and the consequence of that is Cp is equal to Cv. So that's why we again get du by dt is equal to dH by dt for solids and liquids as well. So this is a true statement as well. Next question. 10 liters of water in a vessel at 25 degrees Celsius is heated with a heating rate of 1000 joule per second for 20 minutes. What would be the final temperature of the water? So suppose this is a system. There's a 10 liters of water here, and sorry. So there's a pan and it is heating. So this water at time t is equal to 0 was at 25 degrees Celsius, and it is heated with a heating rate of 1000 joules per second for 20 minutes. So what would be the final temperature? So we need to apply the transient state energy balance here. So we see whatever is accumulated, or you can write the energy balance equation du by dt. So whatever is so we look at this equation here. So in this case, whatever is coming in and coming out, heat in and heat out, in terms of a fluid flowing, that term is 0 basically here, and whatever be the Q is, heating rate is given to us. So heat transfer rate is given to us 1000 joule per second. So we are given Q. There is no shaft applied. So this equation in minus out, or you can write uh, m dot h in minus h out. This term is basically zero because there is no flow of any fluid, and plus q dot minus w s dot. So this is also zero, only q remains. So this is how we get this equation. And u, if you know, we can also write it as mcv t. So cv is specifically to respect to with constant volume, at constant volume. So you can write dmcvt by d small t, or d with respect to, with change with respect to time, and this is again q dot, sorry, and we are given this heating rate, it is 1000 joule per second. We are given are we given this m? So what will be the m? So m will be mass of water. So mass of water will be rho into v. We are given 10 liters, and 1000 gram per liter is the density. So 1000 into 10. So basically 10,000 grams of water. Cv for liquids, we saw that Cv is equal to Cp basically. So we can use the Cp value given here. Firstly, we'll integrate this equation. So uh, all this can come out. So dt by dt is equal to, we can write it here itself, rho v Cp. I've substituted C with Cp and M with rho v. So this is what you get. Now we need to integrate this. Sorry. Now we need to integrate this. So this will be, we don't know the time, we know the time. So this is 20 minutes, and this heating rate given to us is in seconds. So we 20 into 60 will be 1200 seconds. So that is what you get, and this is time t is equal to 0. And we know the inlet temperature, sorry, the initial temperature is 25 degrees Celsius, and the final temperature we need to find out. So if you integrate this, so you get it as t minus 20, sorry, q dot by rho v cp into the integration of this will be t itself, and that will be 1200 into 1200. Okay, so uh, we substitute the values here. So t will come out to be 25 plus q dot is 1000 by again 1000 into 10 into cp is 4.18, and into 1200. So t comes out to be, so t comes out to be 93.7 degrees Celsius. That's what the answer is. We move on to the next question. Concept of energy balance is based upon. Is it based upon conservation of momentum? No. Is it based upon conservation of mass? No. It's based on conservation of energy, yes, because energy can neither be created nor be destroyed, but can be transferred from one form to another, and not on conservation of volume as well, so conservation of energy. Next question. When Q is equal to 0, the system is said to be isothermal. Is this correct? Isothermal is basically the temperature at any point at any time in the system is same. The temperature does not change with time or space. That is called isothermal. But Q is equal to 0 is for adiabatic system. There is no heat transfer from the system to the surrounding. So this is a false statement. Next question. The process in which variables change with time is called as steady state process? No, because steady state process is that in which the over after going through some time the variables have reached the steady have reached you can say they are constant, they do not change with time, so this is not correct. Unsteady state process, yes, correct, the process variable change with time. Transient process, again same, so the correct answer is both B and C. Next question. If there is no temperature change throughout the system at any time, it is called an, what will be the correct answer here? So if there is no temperature change throughout the system at any time, it is called, as we have discussed, it is an isothermal process. Next question. Consider a first order reaction A giving B occurs in a reactor with continuous inlet and outlet streams and which is initially filled with A. The inlet stream has only A and it is completely converted in the reactor. What will be the mole balance equation like for A? So we need to write the mole balance equation for A. So we draw this reactor here. There is some inlet, there is some outlet. But we can say that the inlet stream has only A, so this is pure A. Uh, and uh, and it is completely converted in the reactor, so there is no A in the outlet. Now, initially some A is already present inside, okay, and there is continuous inlet and outlet stream, okay, fine. So, initially filled with A, and there is continuous inlet and outlet, so there will be some accumulation term, okay. Then there is some inlet, there is no outlet, and there is no generation, but there is some consumption because A is getting converted, completely converted into B, but there is no A flowing out, but because it's complete conversion, so there is consumption obviously. So the correct answer will be A is equal to I minus C. So C, option C here. Unit of the accumulation term dN by dt will be, so suppose this is dN by dt change in mole with respect to time. So the correct unit will be mole per second. As I have told you in the material balance equation, all the terms will have the unit moles per second or kg per second. So the most appropriate answer is mole per second here. Next question. H is equal to U minus PV is the correct relation between enthalpy and internal energy. I feel this is an incorrect statement because H is equal to, it is U plus PV, not U subtracting PV. So this is a false statement. The heat content of the system is given by, so as we have studied in the previous lectures, the heat content of a system is given by enthalpy. It can be mc2 delta T, it can be m lambda. The heat content of a system is given by the enthalpy. Next question. For ideal gases, the internal energy is a function of temperature only. Is this statement true or false? What do you think? So for ideal gases, yes, the internal energy is a function of temperature only. This is the correct statement. Why? Because if you look at ideal gases, the particles don't have any intermolecular forces of attraction. So in that sense, the pressure and volume become immaterial. So that's why the internal energy is only a function of temperature, not pressure or volume for the, in case of ideal gases. And also from kinetic molecular theory, you derive this relation as 3 by 2 NKT for a monoatomic gas. So this KBT basically. So this is obviously a function of T only, this internal energy. So it's a true statement. Next question, if there is no difference in temperature between the system and surrounding, then no heat transfer will take place, no mass transfer will take place, heat transfer will take place or cannot say. So the most appropriate answer here will be no heat transfer will take place. So because the driving force for heat transfer is delta T. If the delta T is 0, then Q naught will also be 0. Such cases can also be called as adiabatic systems because there is no temperature difference between the system and surrounding. So heat transfer from system to surrounding or surrounding to system is 0. So this can also be an example of adiabatic system. Next question, the process variable for a steady state process can change with time. I feel this is a false statement because as we have discussed, for unsteady state process or transient state processes, the process variable can change with time. But for steady state processes, these variables do not change with time. This is a false statement. Okay, so next question. An endothermic reaction is taking place in a system. In order to maintain the isothermal condition, as per the basic concept of thermodynamics, which option is correct? So there is an endothermic reaction taking place in a system. So basically delta H is positive. What this positive delta H means or endothermic reaction means is that it is taking heat from the surroundings. Okay, to for the reaction to proceed. So basically, it is taking in heat. So so to maintain the isothermal condition, basically, you need to continuously supply the heat or remove the heat. It will be supply the heat. So continuously you need to supply the heat to keep the conditions isothermal. because in endothermic reaction, as it is taking in heat, the system becomes cooler. So if it becomes cooler, it is away from whatever the supposed desired temperature should be. So you need to continuously supply heat to keep the isothermal conditions. Okay. The saturated, next question, the saturated solution of a compound contains 20 gram per 100 gram of H2O. Uh, uh, 20 gram of that compound per 100 gram of H2O. A test run starts with 8 kg of compound to dissolve in 100 kg of a pure compound, or you can say water. The rate of dissolution of the compound in water is given as Rd is equal to Kn into CSS minus Cs, where K is the rate constant in second inverse unit, and N is the undissolved quantity of that compound at any time t in kgs. CSS is saturated solution concentration and CAS is the actual concentration. So whatever the quantity is dissolved. Okay. What will be the material balance equation for this system? So we write again A is equal to I minus 0 plus E minus C. So we can again write, we can take this statement n, let n be undissolved quantity at any time t. So we write the material balance in terms of n only. So whatever the change in n will be, dn by dt, is anything coming in or going out? No. So these terms are neglected. Now if the whatever is being dissolved, so that is what we write here. So Rd. So you can write it as dn by dt is equal to Kn CSS minus CAS. Now what is CSS in this case? Saturated solution concentration. So this is this concentration given here. So that will be 20 by 100. What will be the CAS? Actual concentration. So we know a test run is starting with, this is the saturated solution compound. If in 100 grams or 100 units of water, if you add the 20 units of the compound, it gets saturated. This is the saturated concentration. So suppose you can uh, you can find the basis of this equation is such that, suppose there is a liquid here, suppose this is 100 units of water, and we know that if we add 20 gram of this compound, this solution will become saturated. So we suppose we add, suppose 10 grams, so this is not saturated. So whatever the rate of dissolution will be, it will basically be the driving force. So what is the driving force? It is the saturated solution minus the actual concentration. If this CAS becomes equal to CSS, there will be no further rate of dissolution. The driving force has died down. So that is what the basis is. So this is the SS, and what will be the CAS? So we know the test run start with 8 kg of compound to be dissolved in 100 kg. So this is 8 by 100. So this is the total amount. So what will be the amount dissolved? So we know that at any time the undissolved quantity is n. So at that time, what will be the dissolved quantity? It will be 8 minus n. So because this is total, you subtract it by n and divide by 100. So that is what the concentration is given here. So we enter these values here. dn by dt is equal to k into n, 20 by 100 minus 8 minus n by 100. So if you solve this, it becomes 20 minus, plus n by 100 kn dn by dt. So this becomes dn by dt 12 plus n by 100 into kn. So this is the answer. Next question. A single effect evaporator is fed with 15,000 kilogram per hour of weak liquor containing 20% caustic by weight and is concentrated to get thick liquor containing 50% by weight caustic. Calculate the rate of thick liquor form. So we draw the schematic here for this system. So this is suppose feed. There is some thick liquor coming out, and there will be another stream here, which will be vapor. Because what is happening here is there is some solution here. Suppose it is we write caustic as S plus water. Suppose, and it is being evaporated here. And what evaporator does is it is reducing the amount of liquid in the solution, and it is sending it off as vapor. So this vapor, suppose this caustic is non-volatile, so this vapor will have no caustic content. So this is pure vapor, and this will have caustic as well as some amount of liquid because not all vapor may have been evaporated. Because it is written here, it is 50% by weight caustic. So it is basically concentrating the caustic in this evaporator is basically concentrating the or enriching the amount of caustic in this solution. So it went from 20% to 50% caustic. So we can write F is equal to, from the overall material balance, F is equal to V plus L. But from this equation we cannot find, we know F but we don't know V and we don't know L, so we cannot find L. So we go for the component material balance. So we write firstly what are the values of the components here. So X, suppose S in F is 0.2, we know, and X of S in L we know is 0.5, and in V, X of S in V is 0 because this is pure vapor. So we can write the component material balance. This is overall material balance. So that will be F into XSF is equal to V into XSV plus L into XSL. So this is 0 basically because this XSV is 0. So F is 15,000 into 0.2. Mind you, this is in kg per hour, and the concentration of the caustic is given in by weight percent only. If suppose this was mole percent, you may have to convert it to get either this into mole per hour or this into mole percent, or this into, if this was given in mole percent, you need to either convert this into mole per hour, or if this is kg per hour, so you can convert this from mole percent to kg percent, whatever way you like. But here the units are consistent, you can see. And L is, we don't know L, into, it is 0.5. So we can compute the value from here, 15,000 into 0.2 by 0.5. So we get L as, sorry, 6,000 kg per hour. So you can see that 15,000 kg per hour went in, 6,000 kg per hour of concentrated liquor came out, and whatever evaporated was 15,000 minus 6,000, which is 9,000. And this had 50% of 50% of this was caustic. So 3000 kg per hour was caustic. Here you can also see that 15,000 into point 0.2 if you write, here also 3000 kg per hour was caustic. So this caustic throughout the system remains same. Whatever coming in is whatever going out, because none of it is whatever is coming in the feed is whatever is going out in the thick liquor as well, because none of it is evaporating in the V stream. So 6000 kg per hour is the rate of thick liquor form. Next question. A pan containing 2 liters of water at 20 degrees Celsius is placed on an electric heater where the heat is supplied as Q is equal to, you can write it as Q dot, sorry, Q dot is equal to 1500 joule per second to increase the water temperature to 90 degrees Celsius. Calculate the time required to raise this temperature. So in one of the previous questions, we saw that we were given the time. We wanted to find out the final temperature. But now we have the final temperature, we need to find out the time required. So we'll write the material balance equation, the energy balance equation again here. So du by dt is equal to Q from the previous question we saw. This will be the resolved energy balance equation. So again from here we can write this as uh, rho v CVT suppose into dt is equal to Q dot, and Cp is equal to Cv for liquids and solids. So we can write this, if we all take this as constant and take out from here, and t is changing with time, so we keep it inside. Dt by d small t is equal to Q dot by rho v Cp. So if you integrate this dt from 20 degrees Celsius to 90 degrees Celsius, and this is Q dot we know 1500 by rho is again, we can take it as 1000 gram per liter. This is volume is 2, and Cp is again 4.18, and again the small t from 0 to time t. So we can again find this out. This will be 90 minus 20, because integration of only this d capital T will be t, and if you put the limit, that will be 90 minus 20, the final thing. And we can compute this value. Sorry, 1794 you can write, and the integration of this will be t only. So sorry, this t comes out to be 70 by 0.1794, which is equal to 390.18 degrees Celsius. Not degrees Celsius, sorry. The unit here will, what would be the unit? So this is in joule per second. This is gram per liter. This is liter. And this is again joule per gram per degree Celsius. So this liter and liter will get cancelled. This will be gram. This gram and from this gram will get cancelled. So it will be joule per degree Celsius. This is joule per second. So this second and this second will get cancelled. Joule will get cancelled. We only get degree Celsius in the numerator. So the units are constant here. So this will be 390.18 seconds. So this is in seconds. You need to convert it into minutes. So we divide it by 60. So we get roughly 6.502 minutes. We divide basically by 60. So that's what it was. Any questions, anybody? So if there aren't any questions, I'll go ahead and close this session for today. Thank you everybody for joining.